Today we'll talk about similar figures, and I'll pop the PowerPoint up in just a second, but I want to start with a little drawing up here to give you an idea what we're talking about with similar figures. We've talked already about congruent figures, right? Congruent figures have exactly the same size and shape. Every angle of one is congruent to every angle in the other. All the sides of one are congruent to the corresponding sides in the other. So congruent, exactly the same size and shape. But is it possible that two figures could be similar, meaning that they're related in a way, but they're not exactly the same? So suppose I got these two triangles up here. I'll call this one A, I'll call that vertex B, I'll call that one C, and then in this other triangle over here, I'll label it with a D, E, F. Okay, so these two triangles could be similar to each other. How do I know if they're similar? Well, I'm going to label them similar like this. I'm going to say that triangle ABC is similar. That's the similarity symbol. It's like the congruent symbol with just a little mustache on the top without the equal sign on the bottom, is similar to triangle DEF. Now, what does that mean? That means that the sides are all in proportion. It doesn't mean that the sides are the same length, right? One triangle is bigger than the other. But if I looked at it, let's say each of these sides were, let's say this was equilateral, and each of these sides were 4, then maybe each of these sides are 3. Okay, so this bigger one is 4/3 the size of the smaller one. But it's only the sides that are in proportion. It's not the angles. It's not like if each of the angles here was 60, this one was going to be 3/4 of 60. That wouldn't make sense. Then this triangle wouldn't add up to 180 degrees, whereas the first one would. So in similar triangles, the sides are in the same ratio. So the sides are what we call proportional, meaning that if I take the ratio of side AB over DE, in this case, right, it's 4/3, and because I made boring triangles, they're all 4/3. All right, that's the same as the ratio of BC to EF, and that's the same as the ratio of the bottom segments, which is AC over DF. So those three proportions are the same. On the other hand, the angles have to be congruent. So if you notice, angle A is the first angle here, angle D is the first angle there. So again, we go with corresponding angles. So angle A is congruent to angle D. Angle B is congruent to angle E, and angle C is congruent to angle F. So now I have 6 things that are true in these similar triangles. This set of sides are proportional. Those set of sides are proportional. Those are proportional, right? And all 3 proportions are the same. And then I've got 3 sets of angles that are congruent. The thing you got to watch in similarity is not everything is congruent anymore. If they were 2 congruent triangles, then all 3 sets of sides would be congruent, all 3 sets of angles would be congruent. Here, because we're talking about similarity, the 3 sides are proportional, the 3 angles are congruent to each other. All right, we can extend this beyond just triangles, right? Here I've got triangles that are similar, but could I have quadrilaterals that are similar? All right, let's draw out a couple of quadrilaterals. Maybe I have one set of quadrilaterals that looks like this, right? That almost looks like a rectangle. Ooh. And then maybe I've got another one that looks like this. That could be a rectangle as well. Maybe each of the sides of the smaller rectangle are a quarter of the size of the larger rectangle. So if this side is 1 and that side is 3, then this side is 4 and that side is 12. And even though the sides are proportional, the angles are still congruent. Right? Because it's a rectangle, all the angles have a measure of 90 degrees. So the sides are proportional, but the angles are congruent. And so I can have quadrilaterals that are similar. In fact, this concept extends beyond just triangles and quadrilaterals into polygons in general. So for polygons in general, I'm again looking for congruent angles and proportional sides. All right, so let's take a look at the PowerPoint that I had put up there for similarity, and we can see there's some stuff that we've already done, drawing on my other board. So there's my similarity. Here's a definition of similar figures. Same shape, not necessarily the same size. Technically, if they're in a ratio of 1 to 1, similar and congruent are the same, but in general, sides are proportional, angles remain congruent. Again, here's the similarity symbol, right? That's the little mustache without the equal sign in the bottom. And the formal definition says that the three sets of angles have to be congruent, the three sets of sides have to be proportional. That's the same thing that we drew on the other picture. All right, that common ratio of lengths is called the scale factor. So this thing here, whatever ratio that is the scale factor. It tells you how they're related to each other. So in those two rectangles that I drew before, depending which one you put first in your similarity statement, the scale factor would either be 1 to 4 or 4 to 1. All right, and so similar polygons are an extension of similar triangles, similar quadrilaterals. The definition being what? Two polygons with the same number of vertices, meaning that you can't have a hexagon be similar to an octagon, right? They have to have the same number of vertices, 1-to-1 correspondence between the vertices of one and the other, such that interior angles are congruent, sides are proportional. So the same definition that worked for triangles, the same definition that worked for quadrilaterals, works for polygons in general. Same number of vertices, angles have to be congruent, sides have to be proportional. Now, you could be presented with two hexagons and some measures for each side, and you could match up the corresponding sides. And if the proportions are not the same, then the polygons are not similar. All right, so how do you prove that triangles are similar to each other? Just like we had for congruence, we've got theorems for similarity. The difference is that the sides are now not congruent to each other, the sides are proportional. So the first one that's up here is side similarity. Sometimes we do emphasize the similarity because there's also a side for congruence. If you're trying to prove two things similar, I'm going to assume that if you say side, you're looking for the similarity theorem and not the congruence theorem, but you will sometimes see textbooks and other tests that emphasize similarity when it's similar, congruence when it's congruent. So this says corresponding sides of two triangles are proportional, the triangles are similar. So this has to be all three sides. So if you have two triangles, all right, and side length A, side length B, side length C, and then another triangle with side lengths of, I'll call them P, Q, and R. In order to use side, you would tell me that the ratio of A over P is the same as the ratio of B over Q, is the same as the ratio of C over R, or if you were going to put them in different order, you would have to have some reason to do that. Like if you knew in what order the triangles were similar, then you could set it up that way. So here's side similarity. All three sets of sides are in the same proportion. Side angle side is similar, except that it says, all right, you've got two sides that are proportional and the angle between them congruent. So it might be that I have two sets of sides proportional, not the third, right? In other words, I don't have the B and the Q in this one. I just got the two sets of sides proportional and the angle congruent. And again, you got to be careful that it's not the angles that are proportional, the angles are congruent. All right, the third one is angle. Right? Two angles of one triangle congruent to two angles of another, then the triangles are similar. There's actually another version of it called angle. AAA. Not what you call when your car breaks down. AAA meaning angle. But think about it this way. If two of the angles are congruent and the triangles measures that up to 180, the third ones have to be congruent. So you can use angle. If two of the angles of one triangle are congruent to two angles of another triangle, then those two triangles are similar to each other. Not congruent, but similar. So how does this work? Let's try to find out. It says, for each figure, find a pair of find a pair of similar triangles. Note the parallel sides. All right, so what are the parallel sides? AE is over here, and that is parallel to BD. Now, how am I going to figure out if these triangles are similar to each other? Well, what do you know about parallel lines? If two lines are parallel, then a pair of corresponding angles is congruent. So here's one. And then the other pair of corresponding angles is there. So those two angles are corresponding angles. Right? Then if you come down the other side over here, again, a set of parallel lines and a transversal, those angles are also congruent to each other. So now I've got a set of triangles with angles that are congruent to each other. Two angles of one triangle congruent to two angles of another triangle. Those triangles are similar. If it helps you to draw them out like this. Okay, so I've got one triangle over here. And I keep hitting the thing that's trying to advance my PowerPoint. And then a second triangle, this is the bigger one, I'll put down here. So I got C, B, D, right? And it's angle B and angle D that I'm interested in. And then the other one also has angle C up at the top, but it's got an angle A down the bottom and angle E over here. And E is the one that's got 1 mark. A is the one that's got 2 marks. Now you notice that angle C is actually congruent to itself. So I could use angle, 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 but why introduce a third one when we can get away with just 2 of them? All right, so if I'm going to mark these off in terms of a similarity statement, I would say triangle BCD is similar to triangle ACE. And the reason for that, angle-angle similarity theorem. All right, so 2 angles of one triangle similar to 2 angles of the other. Where do I get my angles? In this case, from corresponding angles that come from parallel lines. So now they're all starting to come together. All these different theorems that we've worked on prior are now starting to come together. All right, take a look at this one. I want to show these 2 triangles are similar to each other. So it says BD intersects segment AE at point C. Well, that's interesting, but it doesn't tell me anything about them being congruent to each other, proportional to each other, nothing. So again, I've got to kind of rely on information that's given to me from the picture. I can see angle B and angle D are congruent to each other, right? They're both right angles. They have the same measure. They're congruent to each other. There's another set of angles that are congruent to each other, and that is these 2 vertical angles at angle C. Angle BCA and angle ECD. Both of them are vertical angles. If 2 angles are vertical angles, they're congruent to each other. And would you look at that? Now I've got enough information to prove those 2 triangles similar. In the other case, I could have grabbed that angle C up at the top because they were shared. In this case, angle E and angle A are not shared. So I have to just go on the fact that if those 2 angles are congruent, the third ones have to be because the measures add up to 180. So how am I going to write this triangle similarity statement? Triangle ABC is similar to triangle, it's got to start with E. Then I go down to the right angle, which is D, then over to the vertical angle, which is C. So it's ABC is similar to EDC, and again, by angle-angle similarity theorem. All right, let's take a look at another one. This one's got some numbers in it. It says set up a pair of similar triangles and solve for X. I'll bet you the setup of this looks a lot like the problem we just did, in that there's a pair of vertical angles here at angle C that are congruent to each other. Now, how do we set this up? It says ABC is similar to EDC, so maybe that'll help us to set up the 2 triangles in a way that sort of makes sense to us. If you are somebody that looks at it and you want to see them in the same orientation, set it up like this. So we'll call A up here, B is down the bottom, there's a right angle at B, the length of AB is 5, and then C is the one with just 1 mark on it. All right? How does the other one look? The other one is the bigger triangle, and it's called EDC. So E must go up at the top, D is down the bottom, that's the right angle, the side is length 8, angle C is over here, that's the congruent angle. Now, there's a couple of other things in here, too. It says that DC is X, so let's call that X. And then BC must be what's left. So if DC is X, I'm going to call this piece here 12 minus X. Because you realize if the whole length is X, if the whole length is 12, and one of them is X, the other has to be 12 minus X, so that if I add up this 12 minus X and that X, those 2 things add up to 12. So a little math trick that you can use to try to figure out what that missing piece is. So now do you see that I've got these 2 triangles set up in the same order? And now it should be easy to set up a proportion. So the ratio of AB to ED, 5/8, is the same as the ratio of BC, which is 12 minus X, to x. Now, do you have to set it up that way? No, you could do 8 over 5 and x over 12 minus x. That'll work also. You can do side over base, right? You could do 5 over 12 minus x, and then you could do 8 over x. As long as you set them up in corresponding order, it doesn't matter. It'll all work out the same. All right, cross multiply. We haven't gotten to cross multiply in a while. So let's try cross multiplying. I've got, try to come over here. I got 5 times x All right, I'm going to come over to the bottom. Let's try that. 5 times x equals 8 times, and then parentheses 12 minus x, because that whole quantity 12 minus x is what gets multiplied. So let me carry this across. I get 5x equals 8 times 12 is 96. And then add an 8x to both sides. So 5 plus 8 is 13. This is not going to come out pretty, is it? 13x equals 96. So x equals whatever 96 over 13 is. 96 over 12 would have been a great number. But 96 over 13 is the answer. And so you can go back and you can check your work, put those numbers in, and see if you get back out what you planned on. All right, we're going to do a second video with properties of proportions, and then we'll do properties of quadrilaterals after that. So let's stop here for a second. Part 2 is coming up next.